I'm not really sure how to explain this. So integration by parts is pretty darn useful, but it's not part of calculus AB. However, we've found over the past few years that teaching integration by parts helps students see the structure that's going to help them with U substitution. So hopefully by the end of this, you can start to evaluate indefinite integrals containing products using integration by parts. And you can decide when integration by parts should be used. And that's kind of the same thing, but kind of not. So if you had something like x sine of x squared dx, that definitely has a product, just like what we're going to do today. But it's not integration by parts because this is a U substitution, right? This is 1/2 cosine of 2x squared, and then there's a negative out front. So in this case, even though x is being multiplied by sine, that's the remnants, that x is the remnants of a chain rule, not of a product rule. So we need to start to see product rule. We'll get there. Like I said, this isn't really part of calculus AB. So if this doesn't make sense, don't freak out too much. Hopefully it does. But if you get reasonably good at this, you'll be great at identifying U substitution. So way back when, I had a high school math teacher called Mr. Booz, and I'm pretty sure we were like, hey, here's an integral. The integral of u dv is uv minus the integral of v du. And to me, that's a whole bunch of letters, and it was hard to remember. Before I was teaching calculus, I was teaching 5th grade, and I had to go back and relearn everything. And I bought the Calculus for Dummies book. Mark Ryan, shout out, you did great. Love this book. And a lot of good stuff in there. The one thing I use every year is this acronym. And I was actually looking through it today, and he said, it's not from him, it's from some paper in 1983. But I don't know, he introduced it to me. Let me show you where that formula comes from. We'll get back to how this L-I-A-T-E, liate, or however you want to say it. So what we're going to start off with, integration by parts comes from the product rule from derivatives. So we're going to write that out. We're not going to simplify. We are going to rearrange. Sorry, I had to pause the recording to go yell at some small children that I live with. Anyways, so the derivative of two functions, u times v, is u times the derivative of v. And this notation is helpful. So we're going to write dv dx plus v times the derivative of u, du dx. Now, the part that I want to keep, if we go back a little bit, when we do integration by parts, we say the integral of u dv. So that's the part I'm looking for, and it's right here, the integral of u times dv. Can I get a color, please? Thank you. Right, that's the part I'm looking for. So I'm just going to subtract v times du dx from both sides, and then flip-flop because I really like, for lack of a better phrase, the part I'm going to focus on the left-hand side of the equal sign. So now, we're going to integrate everything in a bit, but before we do that, we're going to give dx's. And so instead of u times dv dx, now we have times dx equals the derivative of uv times dx, and then minus v times du dx times dx. Now this dx you can just think of as an infinitesimal, and a tiny change in x over the very same tiny change in x is 1. Or you can think the rate of change of x with respect to x is 1, however you want to do that. And then we'll just toss some integrals in here. So out of this first bit, what's left is the integral of u dv. In the middle, well, we'll deal with that in a moment. And then at the end, we have the integral of v du left over. So look at this middle piece. It's the only thing we really need to look at that needs to be rearranged. And what this says is the derivative of the integral of uv. Well, the derivative with respect to x of the integral of uv with respect to x. And what you should know there is derivatives and integrals are inverses, so just uv pops out. So we're going to do example, but maybe before we go back, after I saw it today, what this really means here is what we're presented with is going to be two things multiplied together, u and dv. And so maybe we do it at the same time. So this is the integral of u times dv. And in order for this to work correctly, we have to choose the correct u. And I don't really know how to say this. It makes complete sense once it makes complete sense. If you have a logarithmic function, that's what this L over here in Liate is for. When you take the derivative of a log, let's say natural log of x, you get 1 over x. You get something nothing like the natural log of x. You have a less complex derivative to deal with. So if you have a logarithmic function, that's what u is going to be. But if you don't have a logarithmic function, maybe you have something else that has a derivative that gets more simple, or the thing you have goes away. Maybe an inverse trigonometric. Because, like the derivative of inverse tangent, well, that's nothing like an inverse tangent. We get 1 over 1 plus x squared, which you can easily recombine with other things. If you don't have one of those, you choose something algebraic. Now, algebraic functions, they get simpler as you take derivatives, but the derivative, let's say, of x cubed is 3x squared. And then maybe you have to do it again. The derivative of 3x squared is 6x. Ooh, this is getting simpler. The derivative of 6x is 6. And so sometimes with integration by parts, you'll have to do it multiple times. Now the last two, these are derivatives. Well, it's just not really going to work, because if you have trigonometric, I wonder if everybody else has to say that slowly. If you have a trigonometric function, you don't want to choose that as u, because the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of negative, it just goes in circles. Likewise with exponential functions. The derivative of e to the x is e to the x, and just keeps going forever. Anyway, so look in here. We're going to integrate x cosine of x dx. Now remember, our job really is, we want to make sure we're good at u substitution. So kind of think through the process. Is x cosine of x a memorized derivative? Like, did you memorize that in the answer to a derivative you know? No, absolutely not. Can you rearrange? Can you combine x and cosine x to get something else? And, also know there. If you had tangent of x, cosine of x, then you could rearrange. There's a chance. But x and cosine are so different, we can't. Is it u substitution? And the answer there again is no. Shoot, that's the wrong place. If it was u substitution, the form we see is the derivative of the input, x squared, involves, this thing out here, x to the first power. So because none of that is the case, we are going to choose, we have no logarithms, we have no inverse trigonometric functions, we have an algebraic function. That comes before trigonometry. So u is x. I'm going to write it up here. And then dv, I'm going to write everything else. So if you look, if u is x, everything else, cosine of x dx, that's going to be dv. So underneath u is equal to x, we need to find a du. That's actually part of the formula. And above dv, we're going to find out what v is. And v is sine of x, because the derivative of sine is cosine, antiderivative. Now, we draw a 7 in here, and that's what I got from that Calculus for Dummies book. This is just a visual organization, so you don't have to remember that the integral of u dv is equal to uv minus the integral of v du. Instead, we can just remember to write things in the correct places and draw number 7. So across the top, u times v, that's x times sine of x. So we're going to write that. And just all by itself, it doesn't have an integral, it's done. Minus the integral of kind of this diagonal of the 7, sine of x times dx. And you'll notice, because, I don't know, how do we say this? When you choose the u, you want a derivative that goes away or gets simpler. And so we chose x, and then that x, we took its derivative, and du which ends up being a much simpler dx, ends up in this integral. So said another way, we have something very simple to deal with, a lot less complex than x times cosine, just sine. Antiderivative of sine is negative cosine, but we're subtracting negative cosine. So x sine of x plus cosine of x plus a constant. So looking at x sine of x, same kind of thing. You should know, well, I haven't memorized that as a derivative rule. I can't rearrange because x and sine are so different. And it's not use substitution because that's not x squared inside sine of x. If that was x squared, we'd do use substitution. So integration by parts. No logarithms, no inverse trigonometric. Oh, x is algebraic, so u is x. And everything else, sine of x dx, that's what dv is equal to. So du is equal to dx, that's the easy one. And the antiderivative of sine is negative cosine. So v is negative cosine of x. And then we draw that 7 to tell us that the first term is x times negative cosine of x. So we'll write negative x cosine of x. And then we're going to subtract the integral along this, of what gets multiplied along this diagonal. So minus the integral of negative cosine of x dx. And, you can write plus cosine, but I'm trying to make it understandable. And so you're supposed to think, well, this part is done, x cosine of x. And over here, I need the antiderivative of cosine, which is sine, and that's a minus and a minus, so just plus sine of x. Don't forget the plus c. All right. X e to the x is also integration by parts. You can tell because this x out front is not the derivative of x, right? If it was e to the x squared, that's what we would be seeing for chain rule. All right, so u is equal, oh my gosh, that came all at once. Well, let's do it slower. So I'm going to choose u is equal to x, and by the way, this x, because it's got to be things that are multiplied. And then dv is everything else, e to the x dx. v is equal to e to the x, because the derivative of e to the x is e to the x. And du is equal to dx. So we'll draw that 7. X times e to the x goes first, minus the integral of e to the x up here times dx. And notice again, we get a much simpler integral. So the integral of e to the x is e to the x. We're all done. So we need plus a constant. Okay. What about x cosine of 3x dx? Well, x and cosine are very different. We can't combine. We don't have that memorized. Definitely integration by parts. So u is equal to x. dv is equal to cosine of 3x dx. Because remember, we never want to choose trigonometric, this t over here. We never want to choose trigonometric functions. So du is dx, and v, is it sine or negative sine? Oh, sine. And don't forget, we need to divide by 3 for that chain rule. So we put in our 7, and our first bit is x times 1/3 sine of 3x, minus the integral of 1/3 sine of 3x dx. I like to put that 1/3 out front. Coefficients get a little bit weird here, so I can just kind of ignore and think, well, what has the derivative sine of 3x? And the answer is negative cosine of 3x over 3. But don't forget, you have a 1/3 there, so we end up with plus 1/9 cosine of 3x. And now we're done, so we'll throw in a plus c. Another thing to watch out for, I just know after watching students for all these years, make sure you're recopying all the pieces. Some people focus on, whatever's new, like you have to redo this integral, but you need to make sure everything is accounted for. So the integral of x e to the x squared that's definitely not something we've memorized. We can't combine because e to something and x are very different, but the derivative of x squared is 2x. So this is actually chain rule or u substitution. So we can just say u is equal to x squared, du is equal to 2x dx. And I've already put in the pieces that I need, so I just get e to the u du. So 1/2 e to the u plus a constant, and 1/2 e to the x squared. Where's my eraser? plus a constant. All right, I think that looks pretty good. What about x natural log of x? Well, I guess really all we're deciding is this substitution or is this integration by parts? And the answer is, well, x and x, neither one is the derivative of the other, because we all know, well, maybe we all don't, but students in my class know u is never equal to x if you're doing u substitution, because all that would change is the letter, but doesn't really change the form. So what else would be an option? Can u be natural log of x? No, because then du would be 1 over x dx. And we don't have a 1 over x. We have an x times dx. So it must be integration by parts. And what should we choose to be u? And the answer is natural log. I'll put it back here. I lost my liate. All the examples so far have had x, but in this case, we're going to do natural log. That means everything else, the x times dx is dv. Du is 1 over x dx, and v is 1/2 x squared. So across the top of that 7, 1/2 x squared times natural log of x is our first term, minus the integral of 1/2 x squared times 1 over x dx. But, x squared over x, one of those x's divides out. So we get a pretty easy integral of x. Again, I like having that 1/2 out front so I can ignore it. Antiderivative of x is x squared over 2 times 1/2. So minus 1/4 x squared replaces our integral plus a constant. Don't forget to recopy 1/2 x squared natural log of x. Last example. I don't know why I like this one so much, but I do. The integral of natural log of x dx feels like you've memorized this as a derivative rule, but you haven't. It's definitely not u substitution, because u can't be x or natural log of x. I guess it's integration by parts, and the only thing in there is natural log of x, so that's u, and dv is dx. U is equal to natural log of x, so du is 1 over x dx, and dv is dx, so v is equal to x. So across the top of the 7, x times natural log of x, and then along the diagonal, we're going to subtract the integral of x times 1 over x, so that's just 1 dx. That's pretty easy antiderivative, x, so we get x natural log of x minus x plus a constant. I hope that helps.